Hey everybody, and thanks for coming to my presentation today. My name is Todd Kautz with the SUNY ESF Global Wildlife Conservation Center. Today I'm going to be talking about wolf predation rates on radio-collared white-tailed deer within the western Upper Peninsula of Michigan, USA during 2009 through 2019. In the state of Michigan, the law requires that the conservation of fish and wildlife populations of the state depend on the wise use and sound scientific management of the state's natural resources. The state also has management plans for both wolf and deer populations. In the wolf management plan, a goal that's specified is to investigate the relationships between wolf and prey populations. Within the deer management plan, the goal specified is to evaluate and consider impacts of predators on deer densities. In recent decades, there have been contrasting population trends for wolves and white-tailed deer within Michigan's Upper Peninsula. Whereas gray wolves have generally expanded in numbers and geographic range from the mid-1990s until 2010, during that same period, white-tailed deer populations appeared to decline, and significantly, hunter-harvest declined from 1995 through 2010. This prompted the question of what is the role of wolf predation in western Upper Peninsula deer population dynamics, which was the purpose of this study. Within white-tailed deer populations, mortality rates are generally the greatest for newborn fawns, especially in their first few weeks after birth. Often, it's that intra-annual variation in fawn recruitment that has the greatest influence on deer population trends. However, population growth is most sensitive to adult female mortality, where each single mortality from an adult female has the greatest potential of any member of the population to influence population growth. Our objective was to estimate the role of wolves as a mortality source for neonatal and adult female white-tailed deer within the western Upper Peninsula. During 2009 through 2019, we monitored samples of adult female and neonatal white-tailed deer within several winter range subpopulations throughout the western Upper Peninsula. These areas were designed to reflect differences in snowfall conditions, which could affect deer vulnerability to predation. Adult deer were captured within 7 winter range populations during January through March. We used a combination of clover and Stevenson box traps. Captured deer were outfitted with either VHF or GPS collared. We monitored daily or weekly survival on VHF collared deer for up to 2 years post-capture, whereas GPS collared deer had direct satellite uplink that would record and report mortality as soon as it happened. Neonatal white-tailed deer were captured within 3 winter range subpopulations during May through June of each year. We used a combination of opportunistic encounters and vaginal implant transmitters to locate fawns. When fawns were captured, they were restrained and fit with a VHF collar, and then they were monitored from the ground and air every 1 to 3 days until 16 weeks old. When we detected a mortality event, we assessed the likely cause and occurrence of mortality using a combination of field and laboratory techniques. Starting in 2017, where bite wounds were present, we would collect DNA swabs to send in for mitochondrial DNA analysis to identify likely predator species. To assess the nutritional condition of deer mortalities, we collected a femur marrow sample. We would assess this in the field using an ocular and texture estimate, and also back at the laboratory using a dry weight analysis. We identified the likely occurrence of predation based on hemorrhaged wounds. Where predation had occurred, we assessed the likely predator species using tracks and scat found at the site, predator hair for microscopic and macroscopic identification, and other signs left by predators such as caching behavior or canine spacing, which we would cross-reference with canine spacing measurements from captured animals within the study area. We estimated deer survival using cumulative incidence functions within each competing risk of mortality agents. For adult deer, we analyzed survival on an annual interval starting from June 1st. For fawns, we estimated survival from birth until 16 weeks old. We used a staggered entry design because we captured individuals throughout the study period that would be entered into our current survival models. However, for adult deer, we used a 14-day delay after capture to eliminate individuals that could die as a result of injury or myopathy from capture. Because we had multiple competing risks within the same survival models, we used the Allen-Johansen correction for competing risk on the cumulative incidence function. We captured and radio-collared 363 neonatal white-tailed deer and observed 166 mortality events before deer were 16 weeks old. Overall, 47% of fawns lived to 16 weeks old. 3.5% of fawns were predated by wolves before they were 16 weeks old. That amounted to 12 total wolf predations, which was about 8% of known cause mortality. Overall, that was pretty minor in comparison to other predators, such as coyotes, accounting for 13% of all fawns, and bears, accounting for about 8% of all fawns, or even bobcats, at about 5% of all fawns. When you account for a small amount of unidentified predation events, the actual wolf mortality rate, assuming that unidentified predations had similar proportions to identified predations, would probably be somewhere about 5% of all fawns born were killed by wolves before they were 16 weeks old. We included 423 individual adult female white-tailed deer within our survival sample. Because some individuals did not live a year and other individuals were tracked multiple years, this amounted to about 600 total deer years of monitoring. During that time period, we observed 175 mortality events. The overall annual survival rate for adult female deer from June 1st was 79%. Of the 21% mortality that occurred, wolf predation was significant, accounting for 8.6% of all deer within each 1 year period. Of the 56 wolf predations that we observed, this accounted for about 42% of known cause mortality. Other significant adult female mortality factors included starvation and disease, coyote predation, and harvest and human vehicle collision. However, all of those combined only amounted to about the same amount of mortality that we observed from wolves. Most of the wolf predation events that we observed on adult female deer occurred during late winter, particularly during March, April, and May. This is typically the time of year that white-tailed deer are in their poorest nutritional condition within the Upper Peninsula, and often there's also snow conditions such as crusted snow or deep snow, which may facilitate wolf predation of adult deer. Within a high snowfall winter range during 2017 through 2019, we had the opportunity to observe wolf predation side by side with common starvation events with adult white-tailed deer to compare the nutritional condition of deer killed by wolves to those that died of starvation. Interestingly, we observed that the femur marrow water content of deer killed by wolves in about 40 to 50% of cases was nearly indistinguishable from deer that had already died from starvation. This could indicate that many deer killed by wolves, perhaps as many as half, were on their last legs and not likely to survive the winter regardless of predation. So to summarize our important findings, wolves were relatively unimportant to neonatal white-tailed deer mortality, only killing about 3.5% of white-tailed deer by the time they were 16 weeks old. However, wolves were the most important cause of adult female deer mortality, accounting for 42% of known cause mortalities, more than any other mortality source. Most wolf predation of adult female deer occurred during late winter, and many deer killed by wolves were in extremely poor nutritional condition. When it comes to wolf predation on adult female deer, it's important to point out that there is variation geographically and among years on wolf predation rates. For example, in 2018 across 4 ranges, we observed from 0 to 16% mortality rate from wolves. By contrast, within the Deerfoot Lodge range, over the course of 3 years, from 2013 to 2015, we observed variation of 0 to 38% wolf mortality rates within the same wintering area. Considering this, our results present a broad overview of the Western Upper Peninsula deer-wolf interaction, but they may not apply specifically in every area or in every year. To return to our initial objective of evaluating whether wolves limit the population of white-tailed deer within the Western Upper Peninsula of Michigan, we compared our predation rates that we observed to general deer population trends within the Western Upper Peninsula during the same time period. On our study, we conducted a continuous deer camera survey with 64 camera sites from 2012 through 2019 within a mid-snowfall region. We observed a sharp population decline of about 50% from 2012 to 2014 during a period of severe winters, and then a subsequent population recovery from 2015 through 2017 during a period of milder winters and also more restrictive adult female deer harvest regulations. These trends match up very well with observed hunter success throughout the entire Upper Peninsula during the same time period, with a decline of about 50% from 2012 through 2015, but then a subsequent recovery by 2017 with the population. It's important to note that the wolf population across the Western Upper Peninsula and the Upper Peninsula in general has been stable since about 2011 at relatively high densities. And so deer were not subjected to different number of wolves during this time period, and it appears that the population, despite declining during some severe winters, was able to rebound to its previous levels. Our results lead us to several conclusions. The first is that wolves are unlikely to limit deer populations in the western Upper Peninsula through predation of neonatal fawns. This tends to agree with other research indicating that other predators such as coyotes and black bears tend to have larger impacts on fawn population compared to wolves. However, wolves could potentially limit Upper Peninsula deer populations through predation of adult females. Killing off 8 to 10% of adult females per year certainly fits within the range of what would be expected as a significant contribution to adult female mortality within ungulate populations. However, it's a little bit difficult to judge how large that observed 8.6% mortality rate from wolves, which we saw, actually is in terms of deer population dynamics, because as indicated by bone marrow samples of deer killed by wolves, a substantial amount of wolf predation on deer may be compensatory to starvation. However, most importantly, the reduced antlerless harvest in the western Upper Peninsula, along with several mild winters, was apparently enough to compensate for whatever wolf predation was occurring and allow deer population recovery after a decline of nearly 50% in the deer population during 2012 through 2014. Therefore, it appears that deer and wolves in the western Upper Peninsula are in equilibrium even at high wolf densities. However, there may be a small margin for hunter harvest of antlerless deer. Thank you for listening to this presentation. If you have any questions or comments, please feel free to email me at todd.m.kautz@gmail.com, or I can take questions during the interactive Q&A session after this presentation. Thank you again, and have a great day.